So hello, everybody. Welcome to the KWFI breakout session. What am I? I'm your host, Jeff Cookie. I'm over here in Swinburne. And as I get a couple of slides here ready, I will tell you that I apologize ahead of time if I'm not as astute as I should be, because just came off a multi-wavelength, multi-telescope, around the world coordinated telescope run, and it only ended a couple hours ago. So I'm a bit weary, I guess is the word. Okay, so KWFI, for those who don't know about it, is a wide field imager for Keck, which is going to be the most powerful camera in the world, which is already pretty cool. It's UV sensitive, so it can get all the way down to about 3,000 angstroms, which is something that no other telescope can do. So that carves out some unique science for Keck. And with this wide field and that UV sensitivity, we'll be able to do things that even 30 meters can't do. So it's now something that keeps Keck at the forefront and makes it, completely makes it unique and powerful for the foreseeable future. There's nothing that can touch this. So that's great. And I think great, and is something that Keck was designed to do back in the day. Please hold 1 second. Sorry about that, Zoom things. Okay, so how about some of the people on the team introduce themselves? You want to do that? That's here. Yes, and I guess we'll start with, is Rich here? Who we got? Let me see. How about Matt? Oh, I think you're muted. No. I think that's my end, maybe.
Matt, we can't hear you.
Matt, you're unmuted, but nothing's coming through.
All right.
How are your dancing skills, Matt?
Okay, so how about, while Matt struggles, how about we have Peter introduce himself, and then Chuck.
Yes, Peter Gillingham, Friday morning in Sydney, and interested to see what comes this morning.
Can you hear me now?
Yes.
Yes.
Ah, technical difficulties. That's weird. Matt Radovan, UC Observatories. I'm an instrument builder, so I'm working with Jeff and the team at Caltech on the overall opti-mechanical architecture of the instrument.
Thanks. And I don't see others that are part of the engineering. Chuck, I guess you introduce yourself. People know you're famous, right?
No. Hi, Chuck Steidel here in Pasadena from Caltech.
And we have Jean on here, part of the team.
Yep, I'm here. Jean Brody, at
Yes.
Swinburne, but physically present in Santa Cruz at the moment.
And Glenn's on.
Hi, Glenn Capsack, also at Swinburne.
Yeah, and I think that might be all. If I miss somebody, just jump in. Oh, and Mark has been heavily involved, Mark Cassis.
Hi, this is Mark. I'm from Keck. I keep an eye on this team.
Keep us in check. And it's actually a really strong team. We've got people from Caltech, UCO, and AAO. And now that I've finally solved my PowerPoint problem, I'm going to share a screen here. At least I hope I solved it. And just go over some slides for people who don't know about KWFI. And these are just some that are just quickly thrown together. As I said, I was observing. So these will just give you some of the highlights of the I think if it loads here. Tell me when you see it, because I have a black screen right now with the Wheel of Death going on. All right.
Black screen here too. Ah, there it is. That's good.
All right, we got something. Success. All right, so KWFI, Keck Wide Field Imager. It is this beast here. It's going to go up in the prime focus cage. Here are the teams that are involved. The logo's on the right there. And just so people know that let's see if we can get this into work. There we go. Oh, this is just saying that we held a science workshop last December, which many of you attended. This is just the people who attended there. I just have those slides still in there. Okay, so this is the prime focus part of Keck telescope. It's a nice hexagonal cage here, which holds the secondary mirror. And it's very similar to the other end of the telescope, which is a Cassegrain. And so as you bring the telescope down, here's your cage, and it goes to the horizon deck there. And there's a module in there that can be rolled in and out. Actually, I'll show it here. So you can probably see the module inside here, where my cursor is, and there's like one module right there. And so those things roll out in and out. You can put the instrument in, and KWFI will be in one of those. And so it's exchangeable, similar to what's done at Cassegrain. All right, so this isn't forwarding like I want. So it's a wide field instrument. So this is the wide field that it has. The marked on here are the current imagers on Keck, Deimos, LRIS, and Mossfire. Mossfire is infrared though. And a potential future Phobos instrument. And that's the field of view is marked on here. And then KWFI is much larger. And this is the 1 degree design, but we're considering different designs. And I'll just go through that a little bit, but I do want to talk about the sensitivity at Mauna Kea and why this is so great, not just wide field, but the UV sensitivity. So here's a spectrum of the night sky. As you can see, this nice spectrum. I put magnitudes here on the left to help you out a little bit. And in the red, of course, it's bright from skylines in the sky, but then as it gets very dark sight, and in the U, it's quite impressive. And so it's very dark sight and has a very high throughput because we're at 4,100 meters or 14,000 feet. And that is better than any other major site in the world, even where the 30 meters are going to sit. So that makes it unique that it can reach these UV very blue wavelengths. So that takes advantage of that. I mean, the only telescope that's there doing this is CFHT. They had a redder U-band, but recently they got a bluer U-band, and that's a 3.6 meters, so it's quite a bit smaller aperture. And they've been doing some great science with that. But then, as we know, we don't know what the future of CFHT is because it'll become MSE, right? So that's on the plans. So this is an excellent site for U-band, and the only other wide field imager on any 8 mirror telescope is Subaru and Piper ScreamCam, and that has no U-band. It only goes to G. So this is untapped real estate or whatever. And Peter here, who introduced himself, has developed a very clean, simple 4-lens design that enables maximum throughput. So this is just lenses here. The first one's pretty large, about 1 meter across, and then we have the 4 lenses. Filters will slide in here, and this is the focal plane. This last lens actually acts as the Deer window, so that saves on yet another some surfaces. And so it has very high throughput. And combined with CCDs that have a high QE, and I'm not sure why I put this slide here, so I'm going to skip for a second. There we go. They have very high quantum efficiency in the blue. It becomes a very blue sensitive instrument, but still has good sensitivity in red, which I'll show you in a minute here. So this is the throughput in Sloan filters. A lot of lines here, but this solid one here is the Mauna Kea atmospheric extinction. And so that's what really dominates and cuts off the blue end here. This dashed line is the QE of the particular CCDs we're looking at right now. And the dotted one is the optics. So convolving all those together, you get these nice throughput here, the colored ones, U, G, R, I, and Z. And overlaid in gray here is what Subaru throughput is. And as you see, they don't have a U band. There's no U throughput here, very, very little. Now this is a scaled transmission. It's actually up to about 50% for them, but when you do an aperture correction, like for flux per second, it's right here. So this is a comparative look, showing you that for a given time on sky, this is how much better KWFI would be over HyperSupremeCam. So even though it's very, very blue sensitive, it's still comparable, if not better in the red. It's similar in Z-band and better in I. One great thing about KWFI is that the focal plane is taking from the heritage of the Zwicky Transient Facility, which is been running successfully for a long time, and the team there at Caltech has done a great job making a wide field, very high quality detector, and that same technology will be used for KWFI. Matt's been working on the Opti-mechanical. He can tell you about that, and this is kind of the housing for KWFI compared to, say, DESI in this particular picture. So it's kind of more of a lighter weight, efficient design. Has a hexapod that controls the flexure and thermal expansion, etc. And I have a cutaway, I think, here somewhere that can show it a little better, but this gives you just kind of a sense of the outer shell of the KWFI. One thing that is, as I mentioned, UV sensitive is KWFI is very UV sensitive, and so this is kind of a zoom in of the U band region. So this is 3,000, atmosphere here, and 4,000 for U band. So this purple is what you would get for KWFI U band or a extended U. What it is, blue, light blue or whatever. This is for Rubin, because that Rubin observatory would be the only other large wide field telescope that could do this in the U band. And it's in the southern hemisphere, obviously, but it, as you can see, its throughput is much weaker. This is a scaled throughput as well, but also shows you that even though it's attempting to get very blue, it still cannot get, beyond 3,300, say, or 32. And that's like most telescopes, but KWFI can actually go quite blue. So this, there maybe even can consider like a UV band or something to try to get this range in here. Peter's nice lens design also helps account for an atmospheric dispersion corrector. And so here are the 4 lenses. This is the front lens. So, light's coming in this way. This is the focal plane in the back. Your 4 lenses cut away here. This is the filter, if you can see my cursor. And instead of having yet more elements come in here to do an atmospheric dispersion correction, which would take away a lot of your throughput, Peter's worked out where that hexapod and some other actuators can move the lenses. Actually moves this one up a little bit and brings this one around to then correct for the atmospheric dispersion depending on elevation angle. And so I think that's quite extraordinary, and it's a novel design. The aim for this is to have very fast readout, which is about 15-20 seconds, and try to have filter exchange within that time. That's what DECAM does, and some other wide field imagers, and that's what we'd like KWFI to do. So we will use the same. We're looking into the same kind of sliding layered filter, pneumatic filter system, just like they have at Pan-STARRS and on DECAM. And or potentially a wheel, if that ends up being something that's very robust and inexpensive. And we're going to have a large shutter made by Bond, which has done like a DECAM shutter as well. So these things are very big, like 2 meters in size, but they can have a accuracy exposure accuracy of 0.1 seconds as they do a kind of guillotine cut across there. So that's also quite impressive. I've used it at that speed on DECAM, and they actually work, which is pretty impressive. Lastly, this is going to be up in prime focus, and when you put this in there, you have to take out the secondary mirror, so you have just this camera. So the idea from the start, and something we're going to explore now, is to have a deployable secondary. So the secondary is in this image is right where my cursor is here. like incoming light, and these are just the lenses to the KWFI and carriage housing. So this is the secondary mirror, and the idea is to have it move out of the way in a hinging action. That way the secondary can just come in and out, and you can just use the telescope as normal when KWFI is in. So that's the hope, and also that secondary will be driven by the hexapod, which actually can provide better focus and image quality control. So that's a quick rundown of KWFI. It's the not only the most powerful camera, but it'll be able to do science, which I have a lot to we can talk about, that it can do that only Keck can do, which I think is pretty impressive. And yeah, and for the foreseeable future, it's also going to keep Keck ahead, even in the era of 30 meter telescopes. And yeah, that's it, I think, for the intro I had. So that was a lot of slides and things. You're probably slide weary for a day like today. I've been at meetings. So any comments or questions at this point? Anyone? Just give you a second here to. All good so far? All right, just you can.
I have a comment.
Yeah, oh, sorry.
You're
Yes.
going to go through some of those science cases in your talk tomorrow, right?
I will, but because it's 7 minutes, not a lot, but I
Yeah.
will. And I'm going to show you a slide here of some of the science cases, and we can have a chat. Because it's on a different talk, that's where I'm loading it up.
While you're doing that, can I ask another question?
Absolutely.
If you were funded tomorrow, fully funded tomorrow, how long would it take to get the instrument built and on the telescope? Or just ballpark?
We can have the engineers weigh in on this, but I think if we fund it tomorrow, some of the items actually take time to order, make, etc. So it would be about, the assembly itself is really straightforward, or in theory. And so it would be probably 3 years. I think if we had money right now. What do you think, Matt?
I think three would be a fast track. I would have said 4 maybe. So it's hard to know, Gene, because of what's going on. First, you got to procure the fused silica, and then you got to get the optics through. And then there's also this issue right now of CCDs, and one of the cost reductions we're looking at is the possibility of some new STA devices, but STA is working with a new wafer foundry. So there's a few things in there that are driving it.
Yep.
But I would say 3 to 4.
Okay. Good. That's the easy part, right? It's the money that's the difficult part.
If you get us more money, we can go faster. That's for sure.
I'm working on it, Matt. I'm working on it.
Right. And so just since we're on that point, you know, because KWFI is a Swinburne, Caltech, UC, you know, Keck partnership, we're utilizing Australia funding to help this. And so we're going to be applying for national grants here and then in the US as well. So that's our track on that note. Okay, so science things. I had it up and now I moved it.
Oh, there's another
Thank you.
hand up.
Yeah, Melissa.
Hi, sorry, I missed most of your talk because I was in a different meeting. Did you talk at all about capturing the shutter timing for precision timing for solar system objects?
So the shutter is accurate to 0.1 seconds.
Awesome.
So does that seem sufficient?
Yes. Sometimes. So I do asteroid tracking. So
Yeah.
sometimes when I go to a new telescope or a new instrument, I'll ask the support astronomer, what is the precision on your clock, and which header keyword is it that's the precise time, and the answer is usually I don't know.
That's it. So if this shutter is the one that we want and would be, it's already been manufactured for DECCAM. And have you used DECCAM?
I have, yes. It's excellent.
Yes. So it's going to be the same, ideally the same thing. And I've taken 0.1 second images, and they're, you know, accurate, and there's like, yeah, it works really well.
Great, thank you.
Sure. Let's see if I can share this.
Can I ask Melissa
Oh, sure.
whether she needs the large field of view as like a search area for some of the work that she does, or what?
My particular science case are the possible impactors. So when they're discovered, we usually get their current orbital position down really accurately. It's just we don't have enough accuracy to be precise in 20 or 30 years from now. So having the observations with Keck and with the Blanco and Gemini and telescopes like that just gives us a longer time and space resolution span of the observation, so we can propagate it out further in time. So when I most often use DECCAM, and my targets are really only usually in one of the amplifiers, one of the chips. I don't use the whole field of view. But you know, if there was a really scary asteroid that we don't really know where it is, having the wide field of view would come in handy. If we weren't really sure where it was, or if it's moving so fast that we can't be really accurate with our predictions.
Yeah, there's some other science cases for asteroids and near-Earth objects that do require the wider field, but I guess yours are pretty well known, right? Yeah. Good.
Thank you.
Oh, sure. Let me share this. Hopefully you see that.
Yep.
So these are some of the science cases that I listed on here. And so they range everything from, you know, high redshift universe to time domain to low redshift universe to solar system, all over the map. And there are a lot more, but you know, it's hard to narrow it down. I mean, there are things like, you know, we have CGM work, and you got stuff we've been looking for DLAs with narrowband decrements instead of the opposite of Lyman alpha emitters. There's reionization, looking for Lyman continuum from galaxies, which is like 28th, 29th, 30th magnitude. So that's hard, but also because because it can only be done redshift 3 to 4. Beyond redshift about 4.5, the IGM is too opaque that you can't see it no matter how big your telescope. If you have an infinite size telescope, you're not going to see it. So you can only do it from the ground from redshift 3 to about 4.5, and that puts Lyman continuum in the U-band. So you have to have a U-band sensitive telescope. And because this has large scale implications, I mean, you want to understand how these things reionize the universe, you need a wide field to map them and to detect them. And they're relatively rare because they, you know, the thought is that they are emitting Lyman continuum with a duty cycle, and plus, you know, orientation issues, et cetera. So they're not as populous as all of high redshift galaxies. There's gravitational wave counterpart follow-up, which is, I think, a really big driver. And as I'll show in my talk, which I could probably even show here, if people want more slides, they probably don't, that most of the searches are with 1 meter telescopes, because that's where the big wide field searches are. And there is Blanco doing some searching, but they can't really reach the ones that are out farther, and especially the ones with the next generation detectors. So it's getting beyond what they can do. And also, you have such a small time window. There's just hours to catch these things, and you got to map a big area of the sky. So you need a really wide field, very sensitive telescope, because fast exposures, of course, are shallower, so the bigger aperture is needed. And so you have to map really large areas, and so that requires a 10-meter class, 8-meter class, 10 meters to do that. And I can show slides if people are interested. And so that's a very strong driver, because there won't be any telescopes to get these other than Keck. So that's kind of interesting. And I mean, Hyperstream Cam can get some, which is great, but Hyperstream Cam is, as we know, on the telescope sometimes. It's not a TOO type thing where it takes a data put on, and with PFS coming on, it's going to be on less and less. And it's, you know, the universe doesn't have gravitational wave events at nighttime when Hyperstream Cam's on, I guess I should say, right? So it's a hard game. So this will be the one that'll get essentially most of them, if not all of them. And then there's a lot of space missions, which I'll talk about tomorrow, that everyone's excited about. And these are wide field instruments, right? Roman, Euclid, and Spherix, Halo, all these other ultraviolet ones. And they are great. They're going to get good infrared and some of the optical, but they kind of die at about 5,500 angstroms. And then there's nothing. And if you're going to have to, to get the blue wavelengths, 3,000 and 5,000 is kind of this gap where there's nothing. You need a wide field instrument that can get down to 29, and there's not really anything. Well, there isn't anything out there to do that. So KWFI will be that too. And on and on. I could talk your ear off on all these different science cases. So if your science case isn't there, which this is just some of them, let me know, and we will. And does anyone want to discuss these science cases or have thoughts about them?
It would be interesting to tick off the ones that are time domain, that require it to be on the telescope more often than just a campaign mode.
Yes. Now, if the deployable secondary is built with the instrument, then that's just a couple minute.
Sure,
change.
but I'm saying that's the driver, right?
Yes, I see for that. I see. Yes. And I have on this point though, I do want to ask people: does anyone does anyone have any science cases, or can foresee even in 5 years a science case that would need the laser for a TOO? It's an important question. I'd like to know. Or dark time in particular, whatever, that kind of, and if you have to think about that, since I just kind of dropped that on you, because that's also an important driver that we're considering.
Well, and the way that TOOs work now is if a telescope is already in laser guide star AO mode, then the answer is yes, for sure. If it's not, then the current rules are that they don't stand on their heads to start it up in laser guide star mode if it's not there already.
Yeah, so if there's an instrument going that isn't in laser mode, then they just don't go, they don't change over, right? Is that what you're saying?
Yeah, I guess the exception might be if they're in natural guide star mode and somebody asks for the laser, I can imagine that even though they don't do that now, that could be on the horizon. It's not that.
Yeah. Mm-hmm.
Excuse me, Claire, this is Peter.
Yes.
But we can have the lasers hot if you like. The lasers can be on all the time now. And so you could switch instruments if you chose to do so, and we do that now, right? The problem, of course, is that you have to have a target list beforehand for Space Command.
That's true. That's true.
But I guess I'm saying you can observe with KWFI and do laser guide star potentially on the same night if you chose to do so, if you had all the elements.
Yeah, good.
Jeff, I wanted to respond a little bit to what Matthew said about TOOs. It goes both ways, right? Like, it's not just would you want to have a TOO with KWFI, but if KWFI is on, can you use the other instruments? And so having the deployable secondary would be critical if you wanted to do that latter mode, if you wanted to get a spectrum.
No, exactly. No, that I 100% agree, and that's I was saying of those, yes, absolutely. So that's the deployable. But of those, would you say if KWFI was on, would you need it to do a laser TOO? That was the question. Yeah, as opposed to just maybe a like a spectroscopy, spectra or something. Yeah. But yeah, no, there's a huge benefit to that. And even on that note, I would like people to think about and maybe input on that Google Doc that I have, science cases that multiplex this, like if the fact that you can take an image with KWFI, those data will be processed through the data reduction pipeline in like a minute. And if you had that kind of information, would you be able to do science where you could then flip out the mirror and do some spectroscopy, things like that? So if those things sound interesting to you, that is something that could be done. And I'd like to hear some science cases on that or things that could drive that. That's also another driver for the deployable.
Yeah, the obvious one is the gravity wave follow-up counterparts, right?
That's right.
If you find it, you want to follow up.
Exactly. Exactly.
In fact, Jeff, maybe even if you do find it, you might want to just even switch to LRES imaging because you get 2 bands at once.
Yes. Yeah, once you've localized it, yeah, once you've found it, that's right.
Yeah, I don't know about the sensitivity gains. Yeah, right. Like if you really want U-band, maybe you don't switch. I don't know. But yes, definitely you would want a spectrum.
Yeah, and having done gravitational wave work, I think the plan would be, you're searching for it, so you need the wide field to find it, and you would be probably searching in U because you have that capability, because that's the part that fades the fastest. You want to catch it, right? You want to catch the rise and the fade. And then you find it and you have some data on it, and then as it's fading, now you go off to LRES and get everything else, right? Yeah, that's right.
Obvious solution, Jeff, is LRES and KWFI are in different telescopes.
Yeah, that's true too. Yeah, and if that's the case, you either do a TOO on the other telescope, right? Or you can use maybe DEMOS if it's on K2, right?
Yeah, Jeff, I'll point out beyond that, maybe it's even you search in optical or U-band, and then maybe you want infrared imaging, right? So then you switch to MOSFire if it's on, at CAS or something like that. There's a lot that could be done.
Yeah. And aside from gravitational waves, though, other science cases that could use this kind of. Now, I would speak to FRBs because that's something I have just experienced in the last few hours. And FRBs are quite exciting, fast radio bursts, and no one knows what they are, and we're trying to find their A counterpart in any other wavelength to figure out what they are. And they're not necessarily localized well at all, so you have to have a wide field. And the optical counterpart is expected to be very faint, like 27, 28 magnitude. So you've got to have some power. And we found some, and we're trying to figure out what they are, but unfortunately the telescopes we have are small and not deep enough. So that's something that can answer that question too, but this is just something that is personal to me, but maybe others might be interested in fast radio bursts or fast transients in general. So fast transients are things that are anywhere from millisecond to hours long, and those require this fast kind of thing. You need to detect them. They're going to be gone in an hour, so you need to find them, process the data, and then get a spectrum all within an hour. And we try to do that with different telescopes, but that's hard, right? You've got one telescope, the data is coming in, you're processing, and then you're trying to trigger some other telescope, and that takes time. But it'd be really good to be able to do it on one. Yeah. I can't see the participants in this mode, so I'm going to get out of screen share. Okay. What are we looking at here? Okay, so does anybody have thoughts, or actually an important question I'd like to ask is, what impact on your science would because right now we have a degree across field of view as a design, but considering smaller fields of view, and what impact on your science would a smaller field of view make? Because some people might have to have something that large, other than the fact that you might be searching 40 square degrees or something, so you need something big is better, but something that you have some physical constraint on the size. I mean, I've gotten a bunch of input on this, but it'd be good to hear anybody else's thoughts that's online right now. If you you had any comments on that. Like, are there certain science cases that need a certain specific field of view? You know, I'm dropping these questions on each, might need a few minutes to think about them. And also narrowband filters, if you want to think about that. The fact that it's wide field is important, and there's a lot of different narrowband science cases that have wide field searches. Line off emitters, line off absorbers, star forming regions in the Milky Way, globular clusters, large galaxies, local galaxies, it goes on and on. I mean, people can put in there, but if there are special narrowband filters you need, also I'd like to have some input. I'm going to put, if you looked at the Slack, there's the page that I put here for some input. I think I'll try to I'll just put it in the chat here for people. So you can go here and start sticking some things, all these questions I've asked, like you can, you know, please inform us on thoughts you have on the design, your science cases, your demands on field of view, filters, you know, arguments for, against, deployable secondary, things like that. Be welcome. There's people on the team, you guys have something that I've not covered so far because, again, I apologize, I'm a bit sleepy, I should say, having observed and observing here only in, you know, hours ago, right? The time zone. So apologies. Yeah.
I'm going to step in and say, on the topic of your filter question, I wonder if there's anybody on this call who has thought about very specific narrowband filters. And we've done this with LRIS in particular. PIs have had their own filters that they've brought to the observatory. And I'm wondering if there's a reason or a future need for maybe a user configurable slot within the filter wheel that might accommodate somebody's specific science.
I think that's already part of the plan, isn't it, Jeff?
Yeah, the plan right now, I didn't say that, is that there'll likely be 8 to 9, probably 8 or 9 slots. And we'll probably have a continuous UGRIZ in there, but there'll be slots that you can just put user filter. So then we'd have to have, you know, storage for that somewhere, right? We put, yeah, take in and out your filters.
Can you remind us what the likely size of the filters is going to be, Jeff? Is it like 350 millimeters or something like that?
I think it's more like 500. I think Peter.
500.
Yeah, Peter, it's the size of the filters approximately. Oh, he's thumbs upping. I think it's more like on 500.
Yes, I think for the 1 degree field, it's pretty close to 500.
It was like 480 or something. They're comparable to the DESI filters within 5% or something like that.
So I can imagine people being interested in like H&K or like a sky mapper kind of narrowband filter set for looking for metal poor stars, for example. And
Absolutely.
There may be some people who would prefer a sky mapper one, and there may be others who would prefer a pristine, which is a little more narrow than even the sky mapper one that's centered on H&K. So
yeah, that's like their little V or whatever they call it, right?
Yeah.
Yeah. Is there, for that purpose though, would a UV filter be good? Because you're probing that metallicity region, right?
It's broad, right? So the narrower you are, the better you are.
In that region, sorry, a narrow one in that region.
Narrow one in the UV, yes.
Yeah.
Probably can't afford to buy any specific application filters for this instrument. They're going to be pretty pricey, so if people really want to do particular science, I think it's going to be up to the individual astronomers to find the money for the filters. And what's that going to be, about 100K per filter, something like that?
50 to 100, that's right. So it'd be a visitor supplied filter if it's a special case, yeah. I mean, yeah, that's right.
It would be nice if we could swap filters with HSC. They're what, 600 millimeters, so we could share between the two.
Yeah.
That's probably going to encourage a slide then rather than a wheel. Because when you get at 600 millimeters and you start talking wheels, there's just not a lot of room in there. So I think the linear slide is going to be the favorable geometry.
And that's the preferred one anyway, I think. This pneumatic slide is just, it's really robust. I mean, it things never fails, and it's very fast and repeatable. So that's nice.
So what we show in the design is basically, it is the DESI slide, and it is, which is the same as the Pan Stars because it was done by the same person. So that's Bruce Bigelow's work, and I actually have all those drawings. So one of the reasons we baselined around that is it just gives us a jump start. So if it's acceptable, we're pretty far down the road on that, which is nice.
Yeah.
Always good to have something that works.
But you know,
yeah, that you know works. Yeah.
Right. That's right.
You've got a hand up there, Jeff, if you want to call on
Thank
Jonah.
you for, yeah, Jonah.
I was going to mention a bit about the field of view and ultra diffuse galaxies. So we've been searching for them in lots of different fields, and they've been discovered primarily in clusters where they're clenched, but they've also been discovered in large numbers in the field, mostly through being alpha-alpha dark galaxies or galaxies that previously didn't have an optical detection. So most of our selection so far in the field comes from large H1 surveys, whereas we also know that there are at least a few ultra diffuse galaxies in the field that are reasonably quenched and don't have this H1 gas associated. So there's some level of need for an optical survey with a large field of view to search the field, maybe less so in the UV, but more in the GRI bands, and find these ultra diffuse galaxies that lack the H1 content have so far been missed, because it is somewhat puzzling as to how we can have these galaxies quenched in the field environment, I think. So I think it would be quite a useful instrument for that.
Yeah, thanks. So I'm gonna, oops, sorry. Go ahead.
I was just going to add that in that case, the bigger field, the better, of course. You're searching, yeah.
Yeah, and I wanted to show people that you know, this is a game-changing kind of depth. This isn't just, oh, it's a deep imager. This is like 29, 30 magnitude depths. I mean, so you got to start thinking like 27 to 30th. So this is the sensitivity here. And so in like GNR, like you're saying, I mean, in 2 hours, you're getting, you know, 28 and greater, and you can almost reach 30 in a dedicated, you know, if you had some special dedicated depth that you need. But it's really, really powerful. So even if you're thinking, okay, I need to go to 28, which is like what is an ultra deep field now, like, you know, the greatest ultra deeps are like 28. And, you know, in 30 minutes, essentially, or 2 hours, and like in an hour, you're there, right? So if you needed to get some area somewhere on the sky, you've got this depth to find these things, or whatever your science is. And then you've got this extra new regime here, right? So this is full on, you know, JBST 30 meter, you know, depths and things. So that's something to consider in your science too. It's a, you know, in the past we thought, oh, 27, 28, that's deep, right? You're going really deep on images. Now it's, you know, you're going to magnitude or more deeper. So that's quite impressive in that context for science. Yep.
Thank you.
Yeah. So
Jeff, I know you can't see hands up at the moment, so
yeah, sorry.
I'll turn my video on. Hang on. So I just wanted to ask on the follow-up of the Lyman continuum detected sources at redshift 3 to 4. Yeah. What would narrowband follow-up be an efficient way to go after them?
If you go deep enough, you know, you're detecting the narrow. Are you saying detecting the Lyman continuum, or potentially these emission lines that could be in the Lyman continuum?
Yeah, either of those, or whether it depends on, I guess, the numbers that you expect, whether you just go straight to spectroscopy for follow-up, or whether it would be an efficient way of either having a narrowband in the U or a narrowband in the equivalent Lyman alpha. And what are your thoughts on that?
I think that is fantastic because what's been done similar to that now has been exactly that with at a very high redshift with was it Supreme Cam or Hypersupreme? Any one of those. They did a narrow band for alignment alpha, a broad band to see that it's a likely, it's alignment alpha the comparative, and then they did a narrow band in the Lyme continuum, or maybe it was broadband, but they did a measurement there, and it produced a lot of galaxies, but it was just one. It was just the bands that they happen to have, and and it's really high redshift because that's the reddest you can go. Yeah, I think it was a narrow band because it was their 3727, I think, band. So, or no, higher. Anyway, sorry, I'm again sleep deprived. So, but yeah, so I think that'd be very powerful because if you had any Lyman alpha narrowband surveys, then you would just have a narrowband where the Lyme continuum is that what you're saying, and then you would detect, yeah.
Exactly. Yeah.
Yeah. That's right. But you would need to go down to like 28, 29. That's deep. So you've got to have a dedicated time.
We tried this with 19-hour exposures with low-res blue with a 340 nanometer filter.
How did that go?
We got really deep. I think you always end up winning with spectroscopy if you know which ones to observe. Yeah.
But I think, the thing is that with this this extra new blue region, you can, there's this whole like redshift 2, 1.5 to 2 Lyman alpha emitters that haven't been done because it's just too blue. And those surveys would happen because that's also like some key transitional time for them. But at that redshift, you have no contaminants. So anything that's emitter is a Lyman alpha emitter because there's just, you're below oxygen and stuff in as far as wavelength space. So you got this like pristine little region where you can do Lyman alpha emitter work. And if people are already working there, which I imagine would be a strong case, any of those observations would then be used for Lyme continuum if you then comparatively put something redder, right, to go after that. So I think that'd be kind of like dual purpose kind of science. Yeah. Yeah, good. And kind of get this off of here. Sharing that, I don't know what I was sharing with you, sorry. All right, well, thanks. Anybody have any other last comments while we have a few minutes here? So the conference has been going pretty well? Workshop, yeah. It is a bit odd that I have the breakout session before I had a KWFI talk, so sorry I had to give you a talk at the beginning. But you'll probably hear me repeat some of this tomorrow, so just, go have coffee or something while I'm giving a talk. No, kidding. But thanks everybody, I really appreciate your attendance and participation. Use that Google Doc site to put some things in there, that questions you have, comments, suggestions, ideas. Anybody on the team have any last thoughts that I haven't covered?
I think you've done a great job, especially under the circumstances.
Thanks for your patience. Yeah, no, all good.
Yeah, thanks, Jeff.
Okay, thanks everybody.
Thanks, Jeff.
Sure thing, yep. Thanks, Mark.
Good job, Jeff.
Hey, now. Is that now? Oh, he must have done it. Hi, how's it going?
Good. How are you?
Good. Good to see you.
Good to see you.
Yeah. So what do you think about KWFI?
It's great. So I think it's good for the transients, right?
Yeah.
So did you make a comparison against the CFHT U-band?
A while ago, not now, but it's something like 20 times faster or something. I don't remember. Yeah.
Yeah.
Something like this. Yeah.
So suppose CFHT can have an infinite amount of time, but you can still win.
I think so because they put what is it, a few hundred hours. Well, no, I think the U-band was 80 hours, or how long did they do that Claude's thing? And you can do that in like 2 hours with KW5. You know, it's like, it's embarrassing, you know, but yeah, it's hard. It's hard for CFHD. I mean, they get great to 27.5, but then after that, it's a lot of work.
Yeah, so just for your information, for Hyperstream Time survey, we collaborate with CFHD and they provide us with U-band data.
The clouds, right?
These ultra deep field and these, clouds.
Yeah, clouds, yeah. Yeah, I know about these data because that's what we talk with. I work with that, you know, Ikuru and others a little bit with that. Yeah. So they have good data. It's great. It goes to 27.5, I think.
27.5, yeah.
Yeah, which is good. But as you saw, that's 5 minutes for. You know, so what are you going to do, right? But do you have used
filter throughput because it's very hard to fabricate U-band filter.
Say again?
So filter throughput, you know, it looks too good to me.
It is high because I used a, what is it called? I don't know. Someone called it like super Sloan or some name. I don't know. So yeah, the filter has very high throughput. But when I just do a regular Sloan average pull off the shelf Sloan, it doesn't go to 3000, right? And it's a little bit lower, you're right. Here, you can see where the G is coming down and it pops up a little bit. It would be more comparable. But it still has really good, but if you look at the QE, I can pull that up, but the QE right at the U-band goes up, which helps a lot. So that, you know, because usually you'll see, you know, well, from your point of view, it's like you're going to the blue and then there's, you know, the U-bands like this, right?
Yeah.
But with that QE, it kind of really matches even. And then the filter I have is I don't know what it was from, something that was more of a little higher throughput, so it peaks up a little bit higher, yeah. Because I was assuming that we would spend a lot of time getting the best U-band possible for this reason. Yeah.
So I ordered 2 HSC filters. One costed, you know, as Chuck mentioned, 100K. So it's very expensive.
Yes.
So if it becomes serious, I'm happy to ask the filter company.
Oh. And there was a good idea to have switching between HSC and KW5 filters, but that does mean we have to buy bigger than we need filters. But if in the long run it saves money, we switch, right? That'd be a good idea. If they meet the same specs.
But soon enough, Subaru is going to, you know, HSC may not be used as often as it could be in 3 years.
Exactly. Yeah, I think like what, 1 year, 2 years, it starts nothing, hardly a little bit.
Years. So I think if you can design to match the HSC filter size, it may cost a little bit more, but you can have access to all of the narrowband filters and the broadband filters.
See, that would be wonderful. So that's a very good motivation. I have a feeling we might be taking on someone's next.
Once again, one filter costs 100K. So.
Yes, and if you have 10, no, this is a really good idea. So we should talk some more because, you know, if we're going to spend 70,000 on a filter, why not spend 100,000 if you get free filters, right? Yeah, I agree. Yeah, good. So again, funding, we'll see what happens with KWFI, you know, see where it goes.
Okay, but it's great to have a U-band filter. Yep.
Yeah. I'll say again.
It's great to have a U-band access from Mount here.
Yeah. So all of the Subaru stuff now just put some U-band, right, with really deep.
Yeah.
I mean, if you want to find dropouts, Subaru goes 28. You need something 29 or more, right?
Yep.
In you. And so it's got to be something deep.
Yeah. So G-band is very fast, actually, but not many people are taking advantage of you know, depth of the blue bands.
Right. Right. Yeah. So I think this would open up a lot of science.
Yeah, as you know, W1st Roman doesn't have a blue band.
Yeah, that's like a slide in my talk. It only goes to 5,500 or 5,000, I think. Yeah, and then there's some future UV satellites, which will go really wide field, but they're 2,800 or something, right? So you got this missing spot, right? Hey, Josh.
Hey, Jeff.
Are we hogging on someone's new? Is this open for someone else, or is this still KWFI?
No, the other session was just wrapping up, so I thought I'd jump on and see if I could catch the tail end of this one.
Yeah, we just finished a few minutes ago. Sorry, but if you have questions or anything, I could help answer.
I was just curious to see, you know, what came out of this. I'll look forward to seeing the recording.
Oh yeah, it's recorded good. So yeah, I think I was telling people I had a DWF friend. I didn't tell them any details, but I had one of these DWF friends just last week, and it's had some continuing observations until like a few hours ago here, right? So that's why I'm a bit off in my awakeness. Actually, I'm not like now who can do this all the time. He observes all night long, stays up awake all day, observes. Like, how do you do this? I don't know.
Did you find anything exciting from last night?
I did. We found 2 FRBs.
Oh, really?
In the same field as a repeater, so 3 FRBs in one field.
Wow, that's amazing.
Unbelievable. And I think we've gotten some other wavelength data on it, so we're going to see if there's any detections, and it's really good. Yeah, it's pretty exciting.
Wow, exciting.
Yeah, it's you know, I can tell you later. It's one of those things where, like last time, it's unbelievable how you could take data for 25 hours and have like 2 minutes of no data, and that's when it happens, right? But I'm serious. This is what happened and yeah, it's just been like that. So you're just like, oh, but keep trying, but some of the other telescopes got data. So yeah.
Very nice.
Yeah. So we'll keep pushing, but it was a weird one because it was on it. Oh, see you, Josh.
Yep. I'll see you later.
Yep. Anyway, it was all online, which was weird though, but it was really good seeing you now. Things like that.
Yep. Okay.
All right.
Thank you very much.
Take care.
Look at sleep.
Thanks. Thanks. Yep. See ya.
Yeah.